There is a question that has haunted humanity since we began to look at the starry sky and wonder about our existence. A question so fundamental that it has shaped entire religions and driven centuries of scientific investigation. And that question is simply how it all began. What was the zero moment of the universe? The instant in which absolutely nothing turned into absolutely everything. And for decades, science has offered us an apparently definitive answer. The Big Bang, that cataclysmic explosive event that would have occurred about 13,800 billion years ago, when all of space, all matter, all energy, and even time itself arose from a state of infinite density and temperature. But what if I told you that one of the most influential and respected scientists of our time, astrophysicist Neil deGrasse Tyson, has fascinating and deeply disturbing arguments to suggest that the Big Bang may not actually have been the beginning of it all, that perhaps our cosmic history is much stranger, much more complex, and much more surprising than we ever imagined. And before we dive into this journey that will literally expand its understanding about the nature of reality, if you are one of those who love to question everything and unravel the deepest mysteries of the cosmos like me, subscribe to the channel because we have even more fascinating scientific revelations waiting for you. Now get ready, because what you are about to discover will challenge everything you thought you knew about the birth of the universe. And let's start by understanding why this question is so revolutionary. When Tyson raises this possibility, he is not just making empty philosophical speculation, he is pointing to something much deeper and technically rigorously. He is showing us that the physics of the Big Bang itself contains within it intriguing clues that there may have been something before, some state of existence that preceded that moment we always call the beginning. And this is not just semantically interesting, it fundamentally changes how we think about causality, about time, about the nature of existence itself. Imagine for a moment that you are watching a movie, and suddenly you realize that what you thought was the first scene is actually the middle of a much bigger story. It is exactly this revolution of perspective that we are facing in modern cosmology. And the fascinating thing is that this is not a completely new idea in theoretical physics, but the way Tyson articulates and presents these possibilities makes accessible something that once seemed reserved only for theoretical physicists in its most abstract equations. He has the rare talent of taking concepts that would normally require years of advanced study in mathematics and physics, and turning them into narratives that any curious person can follow and marvel at. So what exactly is Tyson saying, and why does it matter so much to our understanding of the cosmos? The answer begins with understanding that language itself that we use to discuss origins may be misleading us. When we talk about the beginning, we are implicitly assuming that time works in a linear way with a clear starting point. But what if time itself is more complicated than that? What if time is not a straight line with a beginning and an end, but something more, like the surface of a sphere, where the question, what is the starting point, makes no sense? Because there is no special point, Stephen Hawking used exactly this analogy, saying that asking what came before the Big Bang is like asking what is south of the South Pole. The question presupposes a structure that may not exist in reality. To truly appreciate the depth of this question, we must first understand what the Big Bang theory actually tells us. And perhaps more importantly, what it does not tell us. The scientific history of the Big Bang began not with an observed explosion, but with a surprising mathematical discovery. At the beginning of the 20th century, a Belgian physicist and priest called Georges Lemaitre was working with Einstein's equations of general relativity and noticed something extraordinary. The equations suggested that the universe was not static, as everyone believed, including Einstein himself, but rather that it was expanding. Lemaitre proposed that if you rewind this expansion like a movie played in reverse, you would reach a point where the entire universe would be compressed into a single point, which he poetically called the primordial atom. But the idea was so radical that it was initially met with skepticism until in 1929, astronomer Edwin Hubble made revolutionary observations showing that distant galaxies were in fact moving away from us, and the further away, the faster they were moving away. This was exactly what you would expect. See if space itself was expanding. And then came the most powerful evidence of, in 1964, two radio astronomers, Arno Penzias and Robert Wilson, were trying to eliminate an annoying noise from their antennas and discovered that they were detecting the cosmic microwave background radiation, literally the cooled afterglow of that initial hot and dense state of the universe. Fundamental of modern cosmology, but here's the crucial detail that many people miss. The Big Bang Theory magnificently describes how the universe evolved from that extremely hot and dense initial state. It explains how the first particles formed, how hydrogen and helium were created in the first few minutes through a process called primordial nucleosynthesis, where protons and neutrons combined during a very specific window of time as the universe cooled. How gravity gathered matter into galaxies and stars over billions of years. Years is a spectacularly successful theory about the evolution of the cosmos. The theory's predictions about the relative abundances of hydrogen, helium, and other light elements match perfectly what we observe in the universe. The large-scale structure of the cosmos, with galaxies forming filaments and clusters, also matches the simulations based on the theory. But there is a subtle but profound difference between explaining how the universe evolved and explaining why it began to exist in the first place. The Big Bang takes us to a tiny fraction of a second after time zero. We can trace the history of the universe back to something like 10 to the minus 43 seconds after the start. A number so small, it's practically unimaginable. For perspective, if you divide a second into a trillion parts, and then divide each of those parts into a trillion parts again, and repeat this process a few more times, you begin to approach Planck time. That is the smallest time interval that makes physical sense according to our current understanding. Because below it, the very fabric of space-time must become foamy and quantum in ways that our current physics cannot adequately describe. But the what happened at exactly that time? Zero. What caused that initial state of infinite density and temperature? Where did all that energy come from that eventually turned into all the galaxies and stars and planets? And you and me, these questions remain deeply mysterious. And this is where Tyson's analysis becomes absolutely fascinating. He points out that when we try to apply our physical theories to that exact moment of time, zero, we find something disturbing. The equations literally break down. They produce infinities and mathematical vagueness that physicists call singularities. In physics, this is a clear sign that your theory has reached its limits, that you need a more fundamental physics to describe what is happening. It's like trying to use Newton's laws to describe what happens inside a black hole. It simply doesn't work, because you need Einstein's general relativity to deal with extreme curvature of space-time. Or like trying to use classical physics to describe atoms when you really need quantum mechanics. Similarly, to describe the exact instant of the Big Bang, we would need a theory that we don't yet have completely, a theory that unifies quantum mechanics, that governs the very small with general relativity, which governs the very large and gravity. This still hypothetical theory is called quantum gravity, and physicists have been working on it for decades with approaches like string theory and loop quantum gravity and other more speculative ideas. And it is in this space of scientific uncertainty, in this region, where our known physics falls apart, that absolutely fascinating possibilities arise about what may have preceded or caused the Big Bang that we observe. So what is Neil deGrasse Tyson proposing when he says that the Big Bang may not have been the beginning of everything? Well, he is presenting several theoretical possibilities that physicists and cosmologists have seriously explored, and that are gaining more and more traction as we refine our understanding of fundamental physics. One of these possibilities is the concept of a cyclical or oscillating universe. Imagine that the universe goes through infinite cycles of expansion and contraction. The Big Bang that we observe would just be the expansion phase of the current cycle. Before it, there would have been a previous universe that eventually stopped to expand, perhaps, because the expansion slowed down due to gravity, and then began to contract in a big crunch, where all matter and energy would collapse again at one point or something close to it. This collapse would then give rise to a new Big Bang in starting the next cycle. In this model, there is no absolute beginning of time, just a potentially infinite sequence of universes being born and dying like an eternally beating cosmic heart. And this is not just speculative philosophy. Physicists like Nobel Prize winner Roger Penrose in 2020 developed rigorous mathematical versions of this idea called conformal cyclic cosmology. Penrose worked with ideas about how the geometry of space-time, at the end of a cycle when the universe is old, cold, and empty, could somehow connect with the geometry at the beginning of the next cycle. He suggests that in a very, very old universe in the distant future, when all the stars have died and all the black holes have evaporated through Hawking radiation and only scattered radiation remains, the concept of time becomes ambiguous because there are no clocks or observers to measure it. In that state, the universe could somehow re-emerge as a new hot and dense Big Bang. Penrose suggests that we may even find evidence of these earlier cycles as specific patterns in the cosmic microwave background, which he calls Hawking points, which would be signatures of supermassive black hole collisions in the previous cycle. He claims to have found some of these patterns in data from the Planck satellite, although the scientific community still vigorously debates whether these observations are actually significant or just statistical noise, which seems interesting when you look for patterns in complex data. But the simple fact that we can even formulate these ideas in a testable form is revolutionary. But there is another possibility even more surprising and perhaps more widely accepted among cosmologists that arises from the theory of cosmic inflation. Inflation has been proposed independently by several physicists, including Alan Guth, in the early 80s, to solve some subtle but important problems of the standard Big Bang theory. For example, why the observable universe appears so uniform on a large scale, with approximately the same temperature and density in all directions, even in regions that should be so far apart that they could never have interacted or balanced their temperatures. This is called the horizon problem. Inflation solves this by suggesting that in the first absolutely tiny moments after time, 0, perhaps between 10 to the power of minus 36 and 10 to the power of minus 32 seconds, the universe went through a phase of exponentially rapid expansion, literally doubling in size over and over again in unimaginably small fractions of a second. During this inflationary phase, the universe would have grown by a factor of at least 10 to the power of 26 times. This inflationary expansion would have stretched the observable universe from a size smaller than a subatomic particle, much smaller than a proton, to something the size of a grapefruit, or perhaps even larger in less time than it takes light to pass through an atom. It is an almost absurdly extreme idea, but the predictions of inflationary theory about the pattern of fluctuations in the cosmic background radiation have been confirmed with impressive accuracy by satellites like COBE in 1992, WMAP in the 2000, and Planck in the 2010. So we know that something like inflation probably happened even though the exact details are still debated. But here is the fascinating detail that has profound implications for the question of what came before the Big Bang. Since inflation starts in a region of space, due to a special field called the inflaton field, it may never completely stop. Throughout space, while inflation ended in our region, creating our observable universe with its galaxies and structures, it continues to happen in other regions, creating bubbles of new universes, each with their own potentially different physical laws, because the fundamental constants can settle at different values. when each bubble leaves the inflationary phase. This is called eternal inflation and was developed by physicists like Andrei Lind and Alexander Vilenkin. And I discovered something that I find absolutely fascinating in this idea. From where you are watching now, comment on your city or country, because it is surprising to think that somewhere in this cosmic immensity, there may be other regions of space being born right now through their own local Big Bangs. Eternal inflation implies that our Big Bang was just a local event, the birth of a bubble universe within a much larger space that has always existed in an inflationary state and which continues to generate infinite bubbles of universes, each with its own cosmic history. In this view, the Big Bang was not the beginning of space-time itself, but just the beginning of our particular region of it. It is like a bubble forming in boiling water. The individual bubble has a moment of birth, but the water in SI was already there. And there is yet another possibility that Tyson often mentions that comes directly from the limits of quantum physics and its bizarre implications. On the quantum scale, the vacuum is not actually empty, but boils with pairs of particles, and antiparticles constantly appearing and disappearing in a process called quantum vacuum fluctuations. This is not speculation, but has been measured and verified in the laboratory through phenomena such as the Casimir effect, where two very close parallel metal plates in the vacuum experience a force, because there are fewer quantum fluctuations between them than outside them. Some theoretical physicists, including the late Stephen Hawking, have speculated that the entire universe could have arisen as a massive quantum fluctuation, a fluctuation so large and with such specific characteristics that it did not disappear like normal fluctuations, but continued to expand through inflation, becoming our universe. In this scenario, there was not necessarily anything before the Big Bang in the conventional sense, because time and space arose together from this quantum fluctuation. But this still leaves the profound question of where did this quantum field that was fluctuating come from in the first place? What is the nature of this quantum substrate more fundamental, and why it has the properties it does? And here we come to something that Tyson emphasizes repeatedly, with his characteristic scientific honesty that has made him so respected. The blunt truth is that we simply don't know for sure. These are all fascinating theoretical possibilities and mathematically consistent with known physics. But at the moment, we have no way of definitively testing which, if not any of them, are correct. What we can do is follow the clues that physics offers us, work in the mathematics, develop the theories, and be open to the possibility that our intuition about fundamental concepts, like beginning and existence and causality, could be completely wrong. And that is not science's weakness, but its greatest strength. The willingness to say we don't know yet. But here are the most likely possibilities, and here is how we can try to find out. What makes Tyson's position so refreshing and scientifically honest is that he does not present these ideas as definitive truths, but as genuine possibilities that emerge naturally when we push our physics to the limit. He is showing us that the nature of time itself may be stranger than we imagine. Think about it for a moment. Really contemplate this idea. When we ask what was before the Big Bang, we are implicitly assuming that it once made sense as a concept. But what if time itself began with the Big Bang, or emerged from some more fundamental structure that it is not temporal as we understand it? It is like asking what is north of the North Pole geographically. The question itself may not make sense, because north is defined in relation to the poles, and once you are at the North Pole, you cannot go any further north. Similarly, before, it may not make sense when applied to time itself, rather than events within time. Tyson often uses a powerful analogy when discussing these questions. He says that asking what caused the Big Bang can be like asking what caused the cause of causes. We enter into an infinite regress, which perhaps points not to our ignorance, but to the conceptual limits of causality itself when applied to the entire cosmos, rather than to events within the cosmos. After all, our notion of causality, that every effect has a cause, comes from our experience of events within the universe, where time already exists and flows consistently. But applying this notion to the universe as a whole may be an unjustified extrapolation. Some interpretations of quantum mechanics suggest that at the most fundamental level, reality is not deterministic but probabilistic. Things can happen without a cause in the classical sense. Individual quantum events, like the decay of a specific radioactive atom at a specific time, are genuinely random as far as we know, not caused by anything specific, but just occurring with a certain probability that we can calculate but not predict individually. If this applies to the entire universe, then the Big Bang could have been an uncaused quantum event in the classical sense, arising spontaneously from the fluctuations of whatever exists at the most fundamental level of reality. This idea bothers many people because it violates our deep intuition that everything must have a cause. But quantum physics has demonstrated millions of times in countless experiments that the fundamental nature of reality does not care about our intuitions. It is as it is not as we think it should be, based on our limited experience of the macroscopic world. And there is another fascinating dimension to this discussion that Tyson explores, and that comes from recent developments in theoretical physics. The structure of space-time itself, may be emergent, just as temperature is a property that emerges from the movement of trillions of molecules and does not exist as a concept for an individual molecule, or just as pressure emerges from particle collisions. Perhaps space and time are properties that emerge from something more fundamental. Some theoretical physicists, especially those working on certain formulations of string theory and quantum gravity, work on models where space-time is not fundamental, but arises from a network of more basic quantum relationships called quantum bits or qubits. Information. It's like pixels on a digital screen. Up close, you see discrete individual pixels, but from afar, when there are millions of them, they form a smooth, continuous image. If space-time is emergent, then asking what came before the Big Bang may be like asking what was there before pixels existed. The question wrongly assumes that pixels or time have always existed, when in fact they are just an effective, convenient description of something more fundamental underlying. Tyson also points to the problem of the initial singularity, that point of infinite density and infinite curvature of space-time that appears in classical equations of the Big Bang. In physics, whenever we find infinities, it usually means that our theory is incomplete, that we are pushing a theory beyond its domain of validity. Infinities are mathematical warning signs telling you that you need a better and more fundamental description. No physicist actually believes that truly infinite density or infinite curvature exists as a real physical thing. It is an artifact of using classical general relativity in a regime where quantum effects should dominate, not a prediction about reality. So what actually happened in that first tiny moment before inflation in the Planck regime probably involves physics that we still don't fully understand. Quantum physics of gravity that avoids the singularity and smooths out the beginning of the universe in a way that our current physics cannot adequately describe. Maybe the universe began in a particular quantum state without singularity. Maybe it resurfaced from a previous collapse. Maybe it is a bubble in a larger, eternally inflationary space. These are all possibilities that are being actively researched, and there is something profoundly liberating about this honest admission of current ignorance, rather than pretending that we have all the answers or inventing comfortable answers. Science is honestly saying, these are the frontiers of our current knowledge. Here are the most likely possibilities based on what we know about physics. But we need more data, more observations, more sensitive experiments, and probably fundamental theoretical advances before we can answer definitively. This intellectual honesty, this willingness to live with temporary uncertainty as we work to resolve it, is one of the most admirable characteristics of the scientific enterprise. The philosophical and existential implications of these possibilities are absolutely dizzying when you really stop to contemplate them deeply. If the universe is genuinely cyclical, undergoing infinite expansions and contractions, then everything that exists right now, including you reading or hearing these words at this very moment, including every thought you have ever had, and every experience you have had, has existed infinite times before, in previous cycles, and will exist infinite times again in future cycles, is a form of eternity and recurrence that most religions and philosophies have never even imagined. Not in this specific scientific form, not a transcendent immortal soul, but a material cosmic structure that repeats eternally in cycles. Of course, you would have no memory of previous cycles, because information is probably destroyed or scrambled at each transition of contraction and re-expansion. But the exact configuration of particles that forms you, your brain, your memories, your consciousness, could in principle repeat itself. Some physicists, including Max Tegmark, have calculated the probability of this using statistical mechanics, and although it is astronomically small in any individual cycle, in an infinite number of cycles up to, the unlikely becomes not only possible but inevitable. In fact, it becomes certain to occur infinitely many times. On the other hand, if eternal inflation is correct, and appears to be a natural consequence of many versions of inflationary theory, then there are literally infinite universes bubbling into existence constantly, each potentially with different physical laws. In some of these universes, the gravitational constant may be stronger or weaker by orders of magnitude. The constants that determine nuclear forces may have different values. There may be more or fewer spatial dimensions beyond the three we experience. Fundamental particles can have completely different masses, and only an absolutely tiny fraction of these universes would have the right conditions to allow life as we know it, or any form of chemical complexity that could lead to life. This offers an elegant answer to what is called the fine-tuning problem. The intriguing observation that the fundamental constants of nature seem so perfectly tuned with extraordinary precision to allow complex life. If you change the strength of gravity by just 1%, the stars could not form properly or would burn out too fast. If you change the mass of the electron or the strength of the slightly complex chemical electromagnetic force, including the organic molecules necessary for life, would be impossible. If the strong nuclear force were a little different, atomic nuclei would not be stable or could not form. There are dozens of these apparent fine-tunings and the probability of them all being in the right values. By chance seems vanishingly small. In an inflationary multiverse, we do not need our universe to be special or to have been designed. It is just one among infinities. And naturally we find ourselves in a universe compatible with our existence because we literally could not exist in none of the others to ask the question. It is an application of what is called the anthropic principle in its strong form, the idea that the universe must have life-permitting properties because we are here observing it. But it also means that the Big Bang that we study so carefully with our telescopes and experiments is just a drop in an infinite cosmic ocean, just one bubble among infinite others, each with its own physics and history. And there is an even deeper implication about the nature of reality itself that arises when we think carefully about these questions. If the time emerged with the Big Bang, or if it exists in a larger, more fundamental structure that encompasses it, then our linear subjective experience of past, present, and future flowing in one direction may be just a limited perspective, an illusion of consciousnesses trapped in time of something much more complex and timeless. Some physicists and philosophers interpret Einstein's equations of general relativity as suggesting that past, present, and future can all exist equally simultaneously in an eternal block universe where time is just another dimension like the spatial dimensions, and there is no objective flow. In this view, which is controversial but taken seriously by some thinkers, the Big Bang is not an event that happened in the past and then ended, but a limit of the space-time structure that is always there. Timelessly, you cannot go before it. Not because something in the past prevented it, but because it does not exist before in terms of time within the universe. It is literally like trying to go south of the South Pole geographically. Once you are there, there is no south direction to go because south is defined as towards the pole. And Tyson often emphasizes how these purely scientific questions connect deeply with the deeper questions that philosophers and theologians have asked for millennia across all human cultures. Why there is something rather than nothing is perhaps the most fundamental question. Possible, does the existence of the universe require an external cause? Or can it be in some self-sufficient, self-explanatory way? Does the universe have an absolute beginning in time? Or is it eternal in some cyclical or inflationary way? These questions used to belong exclusively to the domain of metaphysical philosophy and theology. But now, modern physics can offer potentially testable answers, or at least rigorous constraints on which answers are physically plausible, consistent with observations and experiments. This does not mean that science can solve all deep philosophical questions. Some fundamental questions like why the laws of physics are exactly the way they are instead of being completely different, or why there is something capable of obeying mathematical laws in the first place, instead of nothing, may be fundamentally beyond the reach of empirical science because there is nothing outside the universe that we can compare to or test against. But the simple fact that we can even ask these questions about cosmic origins in a scientifically sound way, rigorous approach to mathematics and observations, is an extraordinary testament to how far we have come as a species. And there is something deeply humbling but also inspiring about this scientific journey. We are using minds, brains, that evolved specifically to solve practical problems of survival on the African savanna. Find food, avoid predators, cooperate in small social groups to try to understand the origin and fundamental structure of the entire cosmos. It's like ants trying to understand calculus or quantum mechanics. The fact that we have achieved so much that we can detect the echo of the Big Bang, measure the age of the universe, understand primordial nucleosynthesis is extraordinary and almost miraculous. The fact that there are still deep fundamental mysteries is no shame but a healthy reminder of our cosmic smallness, our humble position in the cosmos, but also an inspiring invitation to continue exploring, continuing to push the frontiers of knowledge. And if all these revelations about the potential nature of the beginning of the universe and what may have come before have blown your mind so much. As for mine over the years studying and thinking about this, leave your like to support this type of deep scientific content, subscribe to the channel, and turn on notifications because we are only scratching the surface of the deepest cosmic mysteries that exist and that are absolutely worth exploring together as a community of curious people. As we continue this intellectual journey through the frontiers of human knowledge, it is well worth asking what future experiments, observations, or theoretical developments could give us clues about these deep questions of what caused the Big Bang and what, if anything, came before. Physicists and cosmologists are not just speculating philosophically from comfortable armchairs. They are actively proposing, and in many cases already conducting concrete ways to test these ideas, test the specific predictions that different models make about the observable universe. There are several promising experimental and observational frontiers where we can look for evidence. One of the most promising involves studying the cosmic microwave background radiation with ever greater detail and precision using ever more sensitive instruments. This radiation, discovered accidentally in 1964, is literally a snapshot of the universe when it was just 380,000 years old, still a cosmic baby in terms of the total age of almost 14 billion years. And this radiation contains subtle patterns, tiny fluctuations in temperature and polarization that carry coded information about conditions even more ancient satellites during the inflationary phase and potentially even before. Satellite missions such as COBE in the 90s, WMAP in the 2000s, and Planck which operated from 2009 to 2013, have mapped these fluctuations with unprecedented precision, with each successive mission revealing finer details, and even more ambitious future missions are being planned, and some already in development, that will study the polarization of the cosmic microwave background with extraordinary sensitivity. If cyclical models such as those proposed by Roger Penrose are correct, it should. Although there are very specific patterns in the background radiation, concentric circles of slightly different temperature that would represent gravitational shock waves from cataclysmic events such as supermassive black hole collisions in a previous cycle of the universe. Penrose and collaborators claim to have found preliminary statistical evidence of these patterns in Planck data, but the scientific community remains divided, with many arguing that they are just statistical coincidences, artifacts of looking for patterns in complex, noisy data, which is called the looking back problem. You can find apparent patterns in any set of data large enough if we look hard enough. We need more independent data and more sophisticated statistical analyses to resolve this question definitively. Another extremely promising avenue is the direct detection of primordial gravitational waves. During the phase of cosmic inflation, just after the Big Bang, quantum fluctuations in space-time itself would have created gravitational waves, ripples in the curvature of space-time that would propagate through the early universe. These primordial gravitational waves would leave a very specific and characteristic signature in the polarization of the cosmic microwave background called B-mode polarization, that is distinct from the polarization created by other sources. Unambiguously detecting these primordial gravitational waves through their polarization signature would be one of the greatest discoveries in the history of cosmology, would be smoking gun direct evidence of inflation, and would give us crucial insights into physics at unimaginably high energies that existed in the earliest moments of the universe, far beyond what any particle accelerator could achieve. Experiments such as BICEP, operating at the South Pole Light Bird, planned by the Japanese Space Agency and others, are searching intensively for these subtle signals. In 2014, there was great excitement and worldwide headlines when the BICEP-2 experiment team announced that they had detected the primordial gravitational wave signal, but unfortunately, it turned out to be a false alarm caused by dust contamination in our own Milky Way galaxy that produced a similar polarization pattern, was an important reminder of how careful we need to be when interpreting data and the importance of independent confirmation. But the search continues with even more sensitive instruments, and when we finally unequivocally detect primordial gravitational waves, it will be absolutely revolutionary. There is also genuine hope that increasingly powerful particle accelerators could give us important clues about fundamental physics relevant to the early universe. The Large Hadron Collider in Geneva, Switzerland, OLHC, collides protons at tremendous energies of 13 trillion electron volts, recreating on a tiny scale conditions that existed a tiny fraction of a second after the Big Bang. Although we cannot directly reach the absurdly high energies of the Planck scale, about 10 to the 19 billion electron volts, which is where quantum gravity becomes important, we can study fundamental particle physics and perhaps discover new physics beyond the current standard model that gives us indirect clues about quantum gravity and the early universe. The discovery of the Higgs boson in 2012 by the LHC was a spectacular triumph, confirming the last missing piece of the standard model. But many physicists hope and even predict that it may be just the beginning. Some theories, including versions of supersymmetry, predict additional particles and phenomena that could emerge at higher energies that the LHC can explore in future runs of operation. And on the purely theoretical mathematical front, physicists around the world continue to refine and develop candidate theories of quantum gravity, that still elusive theory that would unify quantum mechanics and general relativity. String theory proposes that fundamental particles are not structureless points, but tiny, one-dimensional vibrating strings existing in 10 or 11 total spatial dimensions, with the 6 or 7 extra dimensions beyond the 3. We experience curled up, compactified so small that we cannot detect them directly. Different modes of vibration of these strings would correspond to different particles, such as electrons, quarks, photons, and so on. String theory is mathematically rich and elegant, but also notoriously difficult to test directly. Because the scales of relevant energy and size are far beyond our current experimental capabilities. Loop quantum gravity, on the other hand, proposes that space-time itself has a discrete granular structure at extremely small scales, on the order of the Planck length, about 10 to the minus 35 meters. Space would be made of interlocking loops forming a network of quantum relations. Both approaches and others, such as twistor theory and causal quantum gravity, make specific predictions about what would happen at Planck energies, including how the initial singularity would be avoided or smoothed. And some physicists are creatively trying to find ways to test these predictions indirectly. For example, by looking for subtle violations of fundamental symmetries or modifications in the speed of light for photons of different energies that would have traveled cosmological distances. So far, none of these theories have been definitively confirmed, and all still have problems and open questions, but the work continues intensely. But perhaps the most powerful and fundamental tool we have is simply our creative scientific imagination, disciplined rigorously by mathematics and guided humbly by empirical observations. Neil deGrasse Tyson exemplifies this perfectly in his career and scientific communication. He is willing to seriously contemplate radical, unconventional possibilities as long as they are genuinely consistent with what we know about well-established physics, and are in principle testable even if we do not yet have the technology to test them now. He does not accept ideas just because they are philosophically interesting or emotionally comfortable, or because they fit into pre-existing worldviews, but critically evaluates them based on logical evidence and rigorous scientific reasoning. And this is fundamentally the beauty and power of the scientific method as a mode of knowing. It allows us to explore questions that seem absolutely completely beyond our reach, when vaguely formulated but systematically breaking them down into specific testable pieces and gradually patiently building an understanding piece by piece over generations. Just 100 years ago, in 1925, we had no idea that galaxies existed outside the Milky Way. We thought our galaxy was the entire universe, 70 years ago. In 1955, we didn't know about the cosmic microwave background radiation, this echo of the Big Bang. Just 50 years ago, in 1975, we weren't sure about the nature of quasars, those extremely luminous objects in the distant universe. 30 years ago, in the mid-90s, we didn't know if planets existed around stars other than the Sun. And now we know of over 5,000 confirmed exoplanets and counting. Each breakthrough, each discovery opens up new fascinating questions and new possibilities that we couldn't have imagined before. So when Tyson says carefully and honestly that the Big Bang may not have been the beginning of it all, he is not just being provocative for attention or speculating irresponsibly. He is honestly representing where the frontier of cosmological science now stands in 2025, explicitly acknowledging both what we know with great confidence and what we don't yet know but are actively investigating. And this humble intellectual honesty, this willingness to admit ignorance about fundamental questions while methodically working to reduce it, is absolutely fundamental to the scientific enterprise, distinguishing it from pseudoscience and dogmatism. Pseudoscience and mysticism often offer simple, definitive answers to all deeper cosmic questions promising comfortable certainty. True, rigorous science recognizes uncertainty where it exists and works systematically over decades or centuries to reduce it through observations, experiments, and theoretical refinement. Honest scientists would rather say we don't know yet. But here's what we're doing to find out than invent comfortable but unfounded premature answers. So we have finally come to the end of this profound intellectual journey through one of the most fundamental and ancient questions humanity has ever contemplated since we first developed self-reflective consciousness. And what we have learned along this path is simultaneously profoundly humbling and tremendously inspiring. Humbling because it honestly recognizes that despite all our impressive scientific progress over the last few centuries, we still do not have a completely tested definitive answer to what caused the Big Bang or whether there was necessarily anything before it in any meaningful sense than before. Inspiring because it clearly shows that we are asking questions that our ancestors could not even have formulated in such a way. Scientifically rigorous, testable, and developing sophisticated observational and experimental mathematical tools to potentially answer them in the coming decades. When Neil deGrasse Tyson carefully says that the Big Bang may not have been the beginning of everything, he is generously inviting us to expand our imagination and our conceptual horizons to embrace possibilities that challenge our most basic, deeply rooted intuitions about time, causality, and existence. He is patiently showing us that the real universe revealed by careful observation can be much stranger, more subtle, and paradoxically more wonderful than any mythological creation story that our species has invented over millennia. Whether through infinite cosmological cycles of universes being born, dying, and being eternally reborn, or through an inflationary multiverse eternally generating new infinite bubbles of reality, each with its own physical laws, or through mysterious quantum fluctuations, giving rise to everything from a quantum vacuum that is not really anything but rather seethes with potentiality, or through some physics even stranger than, as we further imagine, each of these fascinating possibilities is genuinely supported by consistently rigorous mathematics and is compatible with everything we have observed empirically in the cosmos. The fact that we do not definitively know which, if any, is completely correct is not a weakness or flaw, but in fact a characteristic strength of the scientific method that honestly recognizes the temporary limits of current knowledge while methodically working to expand them. And there is something deeply poetic, almost mystical, about the fact that conscious creatures made fundamentally of carbon-nitrogen, oxygen atoms that were literally forged in the nuclear hearts of stars that died ago billions of years can now seriously contemplate the origin of all the stars and all the atoms in the entire cosmos. We are truly and literally the universe made conscious of itself, capable of reflection, trying to understand its own origin, nature, and destiny. Throughout the recorded history of humanity over thousands of years, people in every culture have looked up at the starry night sky and reverently asked themselves where it all came from, how it began, why anything exists. We have created countless elaborate myths and religions and philosophical systems to try to answer that question. Fundamental question. Now, for the first time in the long history of our species, we have scientific tools that can actually investigate empirically, test through observation, and experiment the first moments of cosmic existence. We can detect and measure the reverberating echo of the Big Bang in radiation uniformly permeating all of space. We can calculate precisely how chemical elements were synthesized in the first cosmic minutes. We can simulate the complete evolution of the universe on powerful supercomputers and see how it corresponds in detail to what we observe, and what we have discovered through this rigorous scientific investigation is that objective physical reality consistently surpasses any fiction we can imagine. A cosmos at least 13,800,000,000 years old, containing at least 2 trillion observable galaxies, each with hundreds of billions of stars on average, and countless planets, all seemingly starting from an almost infinitesimally small, hot, dense state and expanding inexorably into the structured vastness we observe. But here is the truly fascinating ending to this narrative. The more we learn systematically about the cosmos, the more we humbly realize this already incredible story of the Big Bang and cosmic evolution may be just a chapter, a single episode of something even much greater and deeper. And this is precisely what makes science so exciting. Intellectually vital, each well-established answer inevitably opens up multiple new, deeper questions. Each empirical discovery reveals new, more subtle mysteries. We will never reach an end point where we know absolutely everything, because the universe appears to be inexhaustibly complex, structured on multiple scales, and continually surprising. And perhaps this is exactly as it should be from the point of view of keeping curiosity alive. A cosmos that we could completely and perfectly understand at all the details would be less interesting, less inspiring than the real cosmos that continually challenges, surprises, and humbles us. So when you look up at the night sky tonight, or tomorrow, seeing those distant stars and planets shining, consciously remember that every photon of light that enters your eyes has traveled perhaps for years or centuries, or even millions of years through the vacuum of space, that those stars are part of an immense cosmic tapestry whose full story we are only beginning to read and understand, that the Big Bang that apparently created everything we see can to have been preceded by something else, something that we have only recently begun to contemplate with scientific tools, rather than just philosophical speculation. And you are part of this epic story of discovery living in an absolutely extraordinary time, where these deep existential questions are gradually moving from philosophy and untestable theology to genuinely testable empirical science. So keep asking, keep questioning, keep marveling authentically, because it is this inherently human insatiable curiosity that has brought us collectively from the primal fear of thunder and worship of the sun to being able to detect gravitational waves of supermassive black holes colliding literally billions of light years away. Billions of years in the past. The universe is gradually revealing its deepest secrets to us, one by one, and each successive generation adds incrementally to humanity's collective cumulative knowledge, by building on the work of previous generations. Perhaps in your lifetime, you will personally witness the confirmed definitive discovery of primordial gravitational waves from inflation or clear observational evidence of parallel universes in a multiverse, or even the first exciting glimpses of a mathematically sound theory. Completa e empiricamente testável da gravidade quântica, unificando finalmente mecânica quântica e relatividade geral. Essas descobertas potencialmente revolucionárias estão chegando mais rápido agora do que nunca antes na história, porque temos ferramentas observacionais e computacionais cada vez mais poderosas e sofisticadas, e mentes brilhantes dedicadas em todo o mundo, colaborando e dedicadas a desvendar esses mistérios cósmicos profundos. E cada um de nós pode participar significativamente dessa jornada coletiva. Mesmo que não sejamos físicos ou astrônomos profissionais, simplesmente mantendo-nos informados sobre desenvolvimentos, scientists supporting basic science, funding, and carefully cultivating that precious sense of awe we feel when we actually stop and seriously contemplate our seemingly improbable existence in such a vast, ancient, and mysterious cosmos. Thank you very much for patiently accompanying me on this profound exploration of the frontiers of human cosmic knowledge. And always remember that the United Verse is demonstrably stranger than we realize, and most likely is stranger than we can imagine with our cognitive limitations, but that only makes it more worthy of dedicated study and reverent celebration.